Okay.
Okay,
Oh, well, I mean, just use a calculator to figure out what that is, right? And then you put x to the 7/3, and you put y to the 8/3, and then 7 to the 8/3. That's what my bet is.
Yeah, how would you?
Wait, what class are you talking about?
Okay, that's right. Just do that.
Well, I mean, like, that's an honest question because I don't know, like, the background of this class. Well, like, how you guys are, so if that doesn't seem simplified, then let me know, but, I mean,
yeah, we need to wrap this up.
just try that, because you've got redos, right?
Yeah.
And boom, there you go, just redo them.
alright, so what do we got here? What's the answer to this? I am recording. Yes.
Prime over U still, wouldn't it be?
What's that?
Isn't it still U prime?
Yeah, because
U
you
prime over U,
Yeah.
plus C, or sorry, not plus C, just
That's
U
what I
prime
was
over U,
thinking.
right? Yeah.
Trying to break us.
Yeah. Okay, so that's equal to, if I write that U prime as a du dx, that's 1 over U times du dx, right?
Yes.
Okay, so let's come up with the antiderivative rule that goes with this. So how do we do that? Remember what our rules are with that? I mean, what do we do?
Is that a 1 or an L?
That's a 1.
1. That's what I thought. But
And this is a
So you want
this is
us,
a prime.
you want us to quote unquote derive the antiderivative rule?
I want you, yes, I want you, but what's our process when we want to go from, we did this a while ago, we haven't done it in a little while, but this is something I want you to know how to do. This is comparable to setting up a differential equation, right?
Oh.
So what do we do here? We want to put this into differential form first, right? So really what we're doing, let's eliminate, let me rewrite this one, eliminate that part right there. So we've got the derivative with respect to x of natural log absolute value of u equals 1 over u times du dx. First thing we want to do, remember, step 1 is we want to write these derivatives in differential form, right? So what's that involved algebraically? What am I going to multiply both sides by algebraically? No,
Dx du.
dx, right?
Period.
Which is a little bit hokey in a way to be multiplying, but it works. The algebra works. So you can think about this as multiplying both sides by dx, which gives us the derivative of log u equals du over u, right? Now it's in differential form. We're not differentiating with respect to anything, right? Okay, so now what? Right, so there's step 1. And we want to transform a derivative rule into an integral rule. We write it in differential form, and then we
Divide by D and then it gives you U over U, which equals 1.
no divide by d.
You have to take the integral.
We take the integral of both sides. Yeah. So we're just gonna do that, right? Okay, and what does that accomplish?
Gets rid of the D.
Gets rid of the d, right?
Brain.
So that if we take an antiderivative of a derivative, they undo each other. That's the nature of a derivative and an antiderivative, right? And so we end up with the antiderivative of du over u equals natural log u to within a constant, right? Make sense? Okay. And so there's our rule for antiderivative integration of functions of log functions, right? Or that's the one that we get from the log rule for derivatives, right? Okay, so let's put that to work. That's pretty simple. Let's try something like,
Can we just take a step back real quick for a
Yeah.
second, 'cause I'm confused. So, we started with d over dx of natural log of the absolute value of u.
mhm.
What did we achieve by changing it to du over u? Like, what?
We got
Was this
rid
like
of
just a
the,
proof?
we got rid of the x's so we could anti-differentiate both sides and undo the derivative, right? Because if you leave the x's in there, it doesn't really work. It doesn't really work because you need to be able to, well, it just, the antiderivative of the derivative with respect to x of log u, that doesn't necessarily cancel, right?
Okay.
Remember, the differential form of a derivative is just applying the derivative rule without specifically looking at the change with respect to any variable, right? And we can do that stuff, like, we don't have to, let's just remind ourselves something. What is, let's say I start off with y equals x squared plus sine x. Let's take the derivative in differential form. What do we get? On this side, we get dy. Okay, what do we get right there? We get 2x dx plus cosine x dx. So if we want to, we could write it as 2x plus cosine x dx. Right? Okay, why do we get the dx there? Well, because that's the variable that's on that side. Right? What we're doing is what we're really doing is we're trying to figure out what are incremental pieces of this thing as we change each side of this thing with pieces that are infinitesimally small. What's the relationship between those pieces? Small pieces of y are related to pieces of x by that relationship. Okay, it's kind of a way to think about it. Okay? But algebraically, what do we do? Well, if this is dy, if I just divide both sides by dx, I just get what I would have got, what you guys would have told me a long time ago, right? So algebraically, you always have the option of just differentiating with respect to x and then multiplying both sides by dx. Okay? All right, so let's try our new rule. Let's try something like this. What if we want to do, let's say, the integral of, the indefinite integral of 2 over x dx. What's the answer?
So the integral doesn't get rid of the dx?
No, it does. Right. Remember, because this is, when we write this as an antiderivative or an indefinite integral, this is the integrand. And that's just the integration symbol, and that's just the variable of integration. Those are just like bookmarks. This is the part that we're really looking at, right? We're playing calculus Jeopardy with, right? So what's the answer?
Is it 2 over x times t?
Well, we could, okay, one thing we could do is we could pull that 2 out front, right? That might help. What's that look like? 1 over x dx or dx over x? Isn't that our new rule? Right?
Oh, that's line.
That's
Oh,
our new rule.
Oh, you just bamboozled me with information.
Those are equal.
Proposal.
Okay.
Those are equal.
So this is just 2 times
Those are
the natural log of
This, the.
X.
The.
absolute value of x plus c. And why do we need that absolute value there?
Because it may be negative.
Yeah, because the natural log function is only defined for positive arguments, right? Positive values of x in this case. Okay, but if we rewrite that, what could we do with that? What could I do with this 2?
You could, it could become an exponent.
Yeah, I could write it as the natural log of
X squared.
the absolute value of x squared, and then do I need the absolute value bars? No, because if we're confining ourselves to the domain of all real numbers, x squared is always positive, right? And so we wouldn't even need the absolute value bars, we could just leave it like that. Okay? Make sense? All right. How about, let's try another one.
That's a one.
How about something like that?
That's J.
It's joules over 4x minus
You're just changing variables, so I mean, it could be.
So what are we gonna do here?
So you can get rid of the one and put the dx on top.
We could,
But
we could,
Would it just be,
but that doesn't look like a standard
no,
form.
it's just log, natural log 4x minus 1, or parentheses.
Okay, so what are you doing there?
You just.
You're making a u
Yeah,
substitution, right? Okay,
Yeah.
so we make a u substitution, we're just gonna say, let's let u equal what?
4x minus 1.
So then du equals
4.
4
dx.
dx, right? It's in, we're doing the derivative in differential form, right? And so what do we got here? Well, we've got a dx, and we've got, right? So then what's this look like in terms of u's?
So it's
so you have 1 over
1 over u.
4.
Okay, so there's, whoops. You're right, we have a du over u, but dx is really equal, but not to du. What's it equal to? 1/4 du.
1/4.
Put the 1/4 out front.
Say that again.
Right, because really what we've got here is just a dx. So we divide both sides by 4, right? And really what we've got in our substitution is a du over 4. Well, we'll pull the 1/4 out front because that's constant, and then it looks like a standard form, doesn't it? Right? So we just get 1/4 times natural log absolute value u plus c. We reverse the substitution, and we get 1/4 natural log the absolute value of 4x minus 1. Let's just do 4. Right, probably 4, but you get the idea. Okay? Right? Okay, how about, what else can we do? Okay, well, let's do a definite integral. How about, that'd be good. Something like this. What if we want to find the area under the curve x over x squared plus 1 as x goes from 0 to 3. Okay, talk me through this.
U substitution.
Okay, what's my u this time?
Squared minus plus 1.
X squared plus 1. There you go.
Okay, he said like it would be different on like one. Okay.
So what's du? So do we have a complete substitution?
No.
Oh, we do. There's no x's left over.
Because you have an x dx. See?
Right, there's an x dx, right?
Okay.
Okay, so then what's this look like?
Is it always gonna work out this perfect?
So,
No, but that's okay. If it doesn't, we can try to complete the substitution.
1/2 integral du.
yeah. 2 over u.
Okay,
And then 3.
but it's a definite integral, so what do we do?
So you have to change it according to u. So the bottom would be 1
1,
and the
Okay.
top would be
the top is 10. Okay. And so this looks like then 1/2 times what?
log x
Speakers like the temperature jump.
Log of, well, I can just say log of u, right? from where to where?
1 to 10.
1 to 10, right? Okay, and then we'll just evaluate this thing. Well, do I need to put the absolute value bars around this?
No.
I don't, because my values of u are all positive, right? So what do we get then? We just get 1/2 times natural log 10 minus natural log of 1. What's the natural log of 1?
Zero.
Yeah. Right? So we just get 1/2 times natural log 10.
So do you have to get rid of the absolute value bars, like if you can, or does it matter?
You get rid of them if you can.
Like if we don't recognize that, and
Well,
we
you-
just keep it on a test and just don't pay attention to that.
I mean, the natural log of the absolute value of 10 would be a little silly, wouldn't it? I mean, that's just natural log of 10. See what I'm saying?
Yeah.
Okay. So there's our answer. Okay, that's just a number.
Why didn't you have to substitute x squared plus y back in?
Say it again.
Why didn't you have to substitute x squared plus y?
Because we're doing a definite integral, right? And so all we're gonna do is just change the limits of integration. Because I'm looking for is a number this time, right? Okay, what about something like this? Let's try something like, what if we have the integral of yikes, what are we gonna do with that?
Not gonna do that.
No substitution.
Sure.
Well,
Well, take an x out, well, doesn't matter.
We could take a 1 over x. Are we allowed to do that?
Okay.
Well, you can, but, yeah, you mean you factor an x out at the bottom, you mean?
Yeah.
You could.
Sure, it doesn't do anything. No, it doesn't do anything. Never mind.
It's just x plus 1.
Okay.
Double
Yeah, double substitution. Isn't that?
Or do we?
Well, I mean, it doesn't, that's not a standard form, is it? Right?
Or should we just brute force our way through it?
Well,
Start with
you
the
can't just brute force your way through it, but let's think about what's really problematic about that. I mean, there's plenty of things, but what's preventing us from, I mean, there is something here that's causing us more problem than the rest of the stuff. If that were just like an x on the bottom, this wouldn't be that bad, would it? Because then we could just split the fractions. Would you agree? Okay, what makes it problematic is if we have a denominator that's got more than one term. Right? So what would be a good thing for us to do? Even if it doesn't fix everything, what's probably a good substitution for us? Yeah, bottom is u, right? And then we're still going to get something that might be kind of messy, but at least if we can make that work, the denominator is just a u. And so I can always split up any fractions I get and do separate parts, right? And maybe use different rules for each part, depending on what we get. Does that make sense? Kind of strategically why we might think about that? All right, so if u equals x squared plus x, what's du? Okay, so what do we got then?
dx.
Okay, so we've got a
Plus 1 in the dx.
yeah, we've got a dx, don't we? Right. So this is going to look like the antiderivative of 3x squared plus 1, right? Times what else do we get? What's that dx equal to?
du over 2x plus 1.
Okay, du over 2x plus 1. Good, and on the bottom we've got a u, right? So then on the bottom we've got our 2x plus 1, and then we've got, this is all going to be times this is times.
That one over U.
Yeah, du over u. Okay, that's kind of a mess, isn't it?
But you have the integral and d du, so you
Yeah, but that's not a complete substitution. So ideas.
can another
Oh.
substitution.
Oh, whoops, you know what? I wrote this down.
Up with the 2x.
I was just thinking to myself, boy, that's gonna be pretty hard. I can't believe we're giving you this.
X
That's an x cubed on the bottom.
Oh.
Right, so that makes it a lot easier. But just
Yeah.
this, I was kind of having fun with this. So that's gonna make it a lot easier. But what could we do with this?
Make a,
This would have been pretty hard, but what could we have maybe done with this part right here?
Could you have
It'd be-
substitute
We could have divided this out, right? And this would have been a pretty hard one to work. But if we divide that out, we'd have to solve for x in terms of u, right? Which would be tough. That'd be pretty hard to do. You guys can't do that.
Oh.
Can
You
you,
can't do that.
can you do it or see this?
Yeah, I would have used a different technique though. I would have used something totally different. I would have used
Yeah.
like trig substitution on this.
Could you show us how you do
Can
that?
we just do?
Eventually, I'm going to, yeah.
But like right now?
No, not right now. It doesn't fit right now. But if u ends up being an x cubed, how does that change our, that makes things work out great. Then this is almost like cheating. What do we get then?
Oh, this. Oh, come on. Oh, this. Boo.
Yeah, see what I'm saying?
Boo.
So we
Back
just
to
get,
square.
Boring math.
right? So what's that
We
equal
just
to?
have Try.
What's that look like?
Rapidly writes down.
Natural log, right? Absolute value u plus c, which is equal to natural log, absolute value, x cubed plus x plus c. Braden, we need the absolute value bars there?
Yeah.
Yes, we do. Good.
Good job, Braden.
Okay. And let's try, let's see, we gotta get one that's a little tougher here.
We were just doing it, that was tough.
Yeah, you should show us how to do that.
Yeah.
That'd be nice and tougher.
Okay, those are all, you guys can roll. So let's try, okay, here's what I'm looking for.
Braden's like,
Okay, here's what we're looking for. All right, something like,
I don't know, dude. I just hate how there's completely different rules for logs and lines.
okay, this is a good one. Like this one.
Skewed. Okay. Oh, okay. So we just want to do an x,
it's just
the.
x over 1. It's x dx.
No.
Come on, Brayden.
21.
No, I'm going with, so the first thing we're gonna want to do is do the thing, so it's gonna be x squared, x plus 1 squared, I think. Right? On the top? X minus 1.
You can't factor.
Can't factor that?
No, you can't, but you can do something pretty good here.
Substitution.
You could, I mean, we could do, so I'm gonna do this two ways.
Or you want
Let-
to
let's-
expand the bottom.
Well, no, you can't. The bottom doesn't expand, right? It's just an x, it's not x plus 1 quantity squared. But let's go ahead and use a u substitution. And then we'll go back and look and see, okay, now that we did that, is there a way we could have maybe seen a pattern here without having to do that first? All right, so this, I don't think this is the best way, but let's do it this way. Let's go ahead and set up u equals what, obviously?
X squared plus
X squared plus 1. So then what's du?
2x plus c.
2x
Times dx.
dx. Okay, so what have we got here then?
Well, we have an
Got the
X.
dx.
Okay, so we got some stuff,
Some
but
Not all the same.
here's a u, right?
Yes.
Well, how about this?
Can we do that?
That's a u.
That's spicy.
Oh,
Yeah.
I told you.
You see what I'm saying? Okay, so then what is, So then we've got a dx here, we can't do an x dx because that's not being multiplied by this, right? But we have a dx would equal du over 2x. So let's rewrite this thing, right? So this is gonna look like kind of a complicated mess here. We're gonna have a u, everybody agree the top is just gonna be u plus x,
Yes.
right? Times, or over u, times dx, which is, if we solve for dx, that's really
Du over
just,
2x.
yeah, du over 2x, right?
Cross multiply.
Oh.
Okay? That's not fitting grade, is it? Right? No, we can't, because it's not an equation.
You get like,
Yeah, you'd have to just multiply straight across.
Yeah,
which wouldn't
Okay.
really help
but what if I were to multiply this,
Yeah, you multiply straight across the x.
if I just multiply straight across, the x's are not gonna cancel. But look what we get. Inside the integral, pull the du out, and what are we gonna get? Well, on the top, we're gonna get a u plus x. On the bottom, we're gonna get a 2u
2x.
I have a single thing on the bottom, don't I? So I could split these fractions. Agree? You get it?
Keep going.
Okay, do you see where we're going with this?
Yes.
Okay. So if I split these fractions, then one of the fractions, the u's are gonna cancel, and on the other one, the x's are gonna cancel.
Yeah.
Right?
Yes.
Okay, get the idea? But then was our,
You get 1/2
yeah, so, right,
1 over 2u plus 1 over 2x.
this is just gonna be so much easier when we do this the other way. But if we split this up, we're gonna break them into different integrals. So I'm gonna end up with the integral of u over 2ux du, right? Plus the integral of,
Wait, wouldn't, oh, yeah, okay. you
Right.
sounded simplified.
plus the integral of x over 2ux is just 1 over 2u times du, so du over 2u.
Why didn't you just do that before with the u's? On the other one,
What do you mean?
on the other side?
Oh, and these cancel, right?
Yeah.
Okay, good. Okay, but now what? I mean, over here, I've got I can pull the 1/2 out front if I want to, but I don't have a complete substitution, right? I've got x's in there too, right? But what is du over x equal to? Look up here in this equation. In fact, du over 2x equals dx, right? See what I'm saying? So this first one here actually just becomes the integral of dx. Now that is a complete substitution because we didn't substitute. It's just in terms of x's, right?
You say substitution because it's not substitution.
Okay, plus over here, would you agree that when all the dust settles, we're gonna get a 1/2 times the natural log of u,
Yeah.
absolute value of u plus c, but what's u? U is x squared plus 1. Do we need absolute value bars, Braden?
No.
No. Right? And this just becomes x, right? And we'll lump our constants together. Right?
So it's just 1/2.
Okay.
Natural log.
Yeah, but look how much easier this could have been. That's an awkward way of doing this. Let's go back to the original problem. And let's do it again. Okay, let's do it again by just breaking it into two separate fractions, right? Why don't I write this as the integral of
X squared plus 1 x squared.
x squared plus 1 plus x over x squared plus 1, right? If I split that up, isn't that just equal to the integral of dx plus
Kindergold,
x over x squared plus 1 dx.
yeah.
Okay, does everybody see that? That's important, that everybody gets that, to that step, that's comfortable, right? This is the plus sign, this plus sign is that plus sign now. Everybody get it? How much easier is that? Piece of cake, right? Now, this one is just x. Over here, we would use our u substitution, and what would we get? Well, we're gonna get that. Right?
Can you go back?
Yeah. Mm-hmm. Okay. Everybody see that? Okay, that worked out pretty well though, because we happen to have exactly an x squared plus 1 in the top, right? What if we didn't? What if it wasn't so easy to see? What if there was like they were off by a fraction or something? So there's even one more thing we could do with this. And I want you to see that these are all analogous, but this is where you really start to become a mathematician, is when you can see how all these different approaches, you know, are all fine, but they all represent the same line of thought, but which one's most efficient? In this case, that was great. But what if it weren't so simple? Well, we've got, what if the integrand were harder? Whoops. Well, all I really have to do is just divide that out, right? Just simplify that quotient. So we could do x squared plus 1 divides into x squared plus x plus 1 how many times?
This is not a different problem, correct?
Yeah.
Same problem, same
Okay,
problem.
good.
So x squared goes into x squared once, right? Multiply through and I get x squared plus 1, subtract the whole thing, and I just get x for my remainder. So that's just equal to the integral of the quantity 1 plus x over x squared plus 1 dx, right? There, it's split for you. You see that? So what's the moral of the story? Well, if we have a rational function like this, and we have the same degree polynomials top and bottom, divide it out, right? You know you're going to get a constant because you know that the ratio of the leading coefficients is going to be, you know, that's going to be the constant part of the solution, right? Does that make sense? And then you're going to get a remainder probably. That's okay. You get a remainder, that's fine. That's going to end up being a rational function where you're probably going to get a log, coax a log out of that for your solution, right? To within a constant. Does that kind of make sense? Okay. How about,
We've got 3 minutes, I think. That was a good round of calculus.
was, if I could get one more in, I'd feel super awesome about it. Okay, how about this one? What's my u substitution here? X plus 1. What's that accomplish? Not a ton, because it's a linear function of x, and I've got another linear function on the top, but what it does that's very useful is I get a single thing on the bottom then, right? So if we make the substitution u equals x plus 1, we get the integral of du just equals dx, right? So I'm going to get the integral of a u squared on the bottom, a du out there, and what is, I can pull my 2 out front, what's x equal to?
U minus 1.
Exactly. That's much better, isn't it? Now I can split that up into 2 separate integrals, right? If I split the fraction, I've got the integral of 2u over u squared. Well, that's no big deal, right?
Well, you,
Yeah, that's, I'm just gonna, my U substitution is in this one, or my V substitution is V equals U squared, right? What about the other one? Then I've got minus 2 times the integral of du over U squared. Well, that's no big deal, right? That's just U to the minus 2 du. That's just a power rule.
what the hell's happening? What?
You see what I'm saying?
Wait. Is that a complete statement right there?
Well, yeah, I mean, we can solve both of those, but this is gonna be a log. This one's not, right? This one's just gonna be, you could have done this one a long time ago.
Yeah.
This is just power rule.
Yeah.
Right? Well, we'll do another one of those tomorrow, but you get the idea,
Yes.
right? So, that U substitution actually did help there.
I was understanding up until right there.
Well-
Drew a minus sign and then 2 integral.
Oh, unrelated.